Hello everyone. Today we will discuss the dynamic programming concept. Okay, so first of all, I should start stating that dynamic programming is not a software development paradigm. It is not something like parallel programming or competitive programming. Okay, so the programming here refers to actually planning. Okay, so dynamic programming is somehow related with solving the optimization problems, so combinatorial challenges. So that is a way to solve those combinatorial optimization problems. When you have a combinatorial optimization problem, so it means that you have a number of choices and you are trying to find the best. And to find the best choice, what I can do is I can run an exhaustive search over the possibilities, right? But we know that that might be very expensive because usually the number of such number of possibilities that might be exponential and it will be expensive to scan all the space. What else I can do is, so there are some greedy algorithms for some of the optimization problems. We'll be visiting them in the upcoming lectures. With the exhaustive search, it is guaranteed that I will find the optimum answer. But with a greedy approach, it is not always guaranteed to have this best answer. So if you do not want to sacrifice from the optimal answer and still you would like to have a reasonable time-space complexity, then dynamic programming is a nice choice, surely if it fits to our situation. Okay, so with the dynamic programming, what we do is actually we store some of the previous results, and by using those previous results, we compute the next. So that sounds similar, right? So that is something like a time memory trade-off thing. And actually, yes, it is. It can be seen as a another way of time memory trade-off because we will be storing some results, and by using those results, we will be able to compute the next one with ease. Okay, and we will see. But usually, those dynamic programming approaches that they fit well to the situations such that you have a recursive solution. Okay, so you have a recursive solution, but unfortunately, those recursive calls are overlapping. That means, okay, I'm making a call to a previous case, but that previous case is being actually called many times during the recursion. I think that would be understood better with a bad recursion. Okay, so there are good recursions and there are bad recursions. A bad recursion means you are making a call to an instance of your problem again and again. So let's see. So assume, yeah, you know this one very well, I know. So that's the Fibonacci numbers. And when I would like to compute a Fibonacci number, I know that Fn is equal to Fn minus 1 plus Fn minus 2. Then I can simply write such a Fibonacci function, right? With this Fibonacci function, I know that for the initials, F0 is equal to 0 and F1 is equal to 1. So if n is equal to 0, I will return 0. If n is equal to 1, I will return 1. Otherwise, I will call the recursion again. Okay, so I will call the same function, not with n, but with n minus 1, plus I will call it again with n minus 2. Then what will happen? Assume you would like to compute f6. Okay, so for f6, you will need to call f5 and f4, right? So here we are constructing the recursion tree. So F6 calls F5 and F4. And what happens with the F5? So that calls F4 and F3, and F4 that will call F3 and F2. Okay, so you should have already noticed that I am calling F4 2 times here. So that tree is exactly the same one that I have here. But unfortunately, since this is a bad recursion, what will happen is I will be computing these things 2 times, right? So similarly, so that F3, it is the same thing that I have here, right? And for F2, you see, there are many overlaps. So this is an example of a bad recursion, and surely you do not want to spend your resources computing something that you have already computed. For that reason, oh, by the way, the time complexity of this recursion will be 1.6 to the power of n. And why that is so? Because we know when n is sufficiently large, the nth Fibonacci number is greater than 1.6 to the power of n. So approximately, okay? So that's approximately, it is greater than that. And if you would like to see the time complexity of this recursion tree, actually you can count the number of leaves, because what will happen is I will go up until a leaf node, right? And then I will pick the guys which is 1 and 0, all right? And then that will make F2 is equal to 1, and I will continue. And that is why to reach 1.6 to the power of n, I will need that much of F2 nodes, okay? So you can see this actually, so it's equal to F1 nodes as well. So that means the number of leaves in my tree is greater than 1.6 to the power of n. So roughly, so that makes our time complexity for this bad recursion for the Fibonacci numbers an exponential one. Okay. Okay, good. So once you notice that this is not a very good recursion, you would like to improve it. And here is a better one. Now we are incorporating the dynamic programming approach here. Okay, you will see why. So what we said in the previous slide, so we are computing something that we have already computed. Then what would be a solution? What I can do is, whenever I compute something, I write it to a table so that at a later time, when I need to compute another thing, first I will go to that table. If it is already computed, I will go and fetch it, okay? Otherwise, I will compute it. Now, our function is something like that. But notice that now I have a Fibonacci array. So in this Fibonacci array, I will be maintaining the results. Okay, so what is F0? What is F1? What is F2? Whenever I compute a Fibonacci number, I will go to this array and update the value. Okay, so when I would like to compute the nth Fibonacci number, first I will go to this array and check if that nth Fibonacci number has been previously computed. If it has been computed previously, it should be at that location. Okay, if it is computed, then I will return it. Otherwise, I will check again. Okay, so if n is equal to 0. If n is equal to 0, what I will do, I know the result. I will immediately go to the first position of this Fibonacci array and write it there 0 and return this value. And similarly, if n is equal to 1, I will update the Fibonacci array 1 with 1 and return it. Other than that, what I will do, the same line. Okay, so the Fibonacci array at position n is equal to Fibonacci, call the Fibonacci function with n minus 1, plus call the Fibonacci function with n minus 2. And at the end, I will return Fibonacci array n. This is actually not that much different than the previous recursion. The only thing is, whenever we compute something, we keep it as an array. So let's try to trace this function on this tree. Okay, again, I'm trying to compute f6. Okay, so for f6, I start here. Okay, so f6, so that means this is my Fibonacci array. Okay, so that's 0, 1, 2, 3, 4, 5, and 6, and all the locations. Everything is empty now. Okay, so this is my Fibonacci array. I'm looking for Fibonacci 6, f6. Okay, so I go to that position and see that it is empty. Okay, then I will not be returning its value. Is n is equal to 0? No. Is n equal to 1? No. Then what I need is, I need to call the same function again with Fibonacci 5 and minus 1 and Fibonacci 4. When you call, surely you will be calling the Fibonacci 5 before Fibonacci 4. So that means the recursion will go from here. So for f5, same story. You will need f4 and f3. And again, f4 is called before f3. So that is why you will make these calls. Okay. So maybe it is better to show that. Okay. So these are actually have not been called yet. Okay. So I'm trying to follow exactly what the function does. And then f3 will give a call to first f2, okay? And f2 will give a call to f1. When it is f1, what will happen? So it will say that, okay, so f1, I will write 1 to the Fibonacci array first position and return. And when f1 returns, f2 will need f0, okay? And f0 is here, so I will write 0 to that position. Okay. Now I have f1 is equal to 1, f0 is equal to 0, and this Fibonacci array, and what will happen is Fibonacci array 2 will be equal to 0 plus 1 is equal to 1, and it will return to here, okay? Now for f3, f2 has been already computed, it is there. How about f1? So I go to my table and see that f1, yes, it's already there. So that means, you see, you are no more creating anything other than a lookup at those positions. So this will make, so 1 plus 1 is equal to 2, and this will go in the same way. But at the end, whenever you reach here, so you will see that, so you will not be making a call to a Fibonacci 4 recursion because Fibonacci 4 will be already there. So that is why you will go and fetch it up. So now that is a better recursion. Why? Because you see, you are maintaining, allocating space. And what is the size of this space? So it is ON, right? And what is my time complexity? My time complexity is just linear now, right? So with this dynamic programming approach, I have ON time and ON space complexities. Okay. Better than the previous approach where my complexity was exponential. But now, when I would like to compute the 1 millionth Fibonacci number, I will need a huge array, right? So, and I don't want this. And actually, I don't need to maintain such a big array. So you just improve it with a better dynamic programming, which will provide you still the linear time, okay? But the space complexity will be constant instead of linear. So it is very easy, right? So I don't need to keep track of anything other than the last two items. Okay, so I will call them the back one and back two. So, okay, I have the back one value. So let's make correct. So that's back two, and this is back one. Okay, and I'm curious about what is here. I will sum the previous two guys, okay, and update this one. So when I update it, so back two will become back one, and back one will be my current item, and then I will compute the next guy. Okay, so that's it. Initially, back two is equal to 0. I start with 0, and back one is equal to 1. 0 plus 1, that is equal to 1. And now 1 plus 1, that is equal to 2. 2 plus 1 is equal to 3, and that goes on. Okay, so easy. So with this dynamic programming, now I have only two cells, an array of size 2 or two variables, whatever you say. So that means my space complexity is constant, and the time complexity, still I will need to iterate from I is equal to 2 to n, so that will be a linear time complexity. Okay, now I guess we are fine with the basic idea behind the dynamic programming. Dynamic programming here is a very good choice because for the Fibonacci calculation, I have a recursion, and in this recursive definition, the subproblems overlap very significantly. And to avoid this, whenever you compute a subproblem, the result of a subproblem, you just record it in the dynamic programming table. In this toy example, our dynamic programming table is composed of just two items, back two and back one. In the previous dynamic programming version, so it is an array of n items, right? So these are one-dimensional dynamic programming arrays. And we will see some more examples. So next one. I hope this would be more interesting. Okay, so I am given a sequence of some coins. Okay, so but these coins are given to me in a specific order. Okay, so I cannot change their positions. Since I cannot change their positions, okay, so C1, C2, C3, so they arrive in this order. And what I can do is, what I would like to do is, I would like to pick the ones that will return the maximum total sum. Okay, so among C1, C2, C3, C4, so let's say C5 and C6, I say that, okay, so I know the values of these guys, and I say that, okay, so I will pick this one, I will pick this one, and I will pick this one, and this will be the maximum. What else I could do? For instance, can I take this one? No, I'm not allowed because there is a constraint. Adjacent coins cannot be picked up, okay? So you cannot pick up C1 and C2 at the same time, or C2 or C3 at the same time. So this is not allowed. The question is, what would be the maximum total sum? Notice that I am looking for the optimal solution. Okay, so the optimal solution. And for this optimal solution, one way I can follow is I can try all possibilities confirming this constraint. Okay, that is one case, but this will be a lot of cases. Or otherwise, I can benefit from the dynamic programming. How we can do this? So let me try to sketch it. Okay, so that's C1, C2, C3. Okay, and then at some position there is Ci. Okay, and then I have Cn. Okay. If I know the result, the answer for the previous guys, then I can use this result to generate the next result. What I mean is, okay, so for instance, for Ci, what can happen? So there is the Ci minus 1, Ci minus 2. If I know this result, okay, so the maximum sum from C1 up until Ci minus 1, I will call this Fi minus 1. Repeating again, Fi minus 1 means the maximum total sum that I can get from the first coin up until and including the I minus 1. I know this value, okay? And again, similarly, I know Fi minus 2. What can happen? So for the Fi minus 2, if I know the Fi minus 2, then I am allowed to pick Ci, skipping Ci minus 1. So that means for Fi, okay, one possibility is go to Fi minus 2 and please add Ci. Why I can do this? Because I know that Ci minus 1 is not here. Or I can say that if I know the Fi minus 1, so I can just keep it as is, okay? For the Fi minus 1, I know the maximum solution that includes I minus 1. Then I cannot pick Ci, so that is why I can just keep it as is. Okay. Repeating again, so Fi denotes the maximum sum that you can obtain with the previous with the I coins where I is included. Okay, so with the Fi, I is included. Okay, once I have defined this relationship, I mean actually it is this one, Fn is equal to the maximum of Fn minus 2 plus the current coin, or directly the previous n minus 1, the sum of the n minus 1 coins, and I do not include Cn. So one of these guys, okay? So once I have this solution, I can just create a recursion. What is my F0? If I do not have any coins, the sum will be 0. And what is F1? Since I have only one coin, so F1 will be equal to C1. So let's see this on an example. Okay. Okay, so let's trace this. What am I given here? Okay, so I'm given these coins, 5, 1, 2, 10, 6, and 2. Okay, so initially, if I do not have any coins, my maximum sum is equal to 0. I know it, right? And for only one coin, when I have 5, what I can do is I can just go and pick this guy. So that is why F1 is equal to C1 is equal to 5. Now, I would like to compute F2. What can happen? For F2, I can go to two previous guys. So I will go to the previous one. Okay, so I will, sorry guys, I need to delete this first. Okay, so I will follow it. Okay, so for this one, I'm trying to compute F2. Okay, so I will go to the previous one. So it is 5. I can just directly copy 5 here. What else I can do? I will not pick the previous one. Go to F0, right? And at F0, I can just add myself. Okay, so 0 plus 1, 0 plus 1 from here, or directly 5. Which one is better? 5 is better. Then that means if you have just two coins, 5 and 1, the best solution is you will go to the best solution is just picking the first one, not the second one. Now we have this coin as well. Okay, so 5, 1, 2. What can I do? So I can go to the position 1. I have 5 here, and 5 plus 2, so that will make 7, right? So it can be 7, or I can just go to the previous position and copy it, which is just 5. So 7 is better, so you put 7 there. Now I will continue with 4. So for position 4, I will check the maximum value that I can get at position 2. So that's equal to 5. And 5 plus 10, that's equal to 15. Or I can go to the previous position and just copy it. So that is 7. Which one is better? 15 for sure better. So you write it there. Okay. And you go to the next one. Now I would like to compute this guy. Okay. For 5, I will go to position 3. So that gives me 7. 7 plus 6, that will be equal to 13. Or I can just immediately copy 15. So surely 15 is much better. You put it there. And the last step is, so for the last step, okay, so that is 2. I will go to position 4. What I have at position 4 is 15. 15 is the maximum sum I can have with these guys. I will skip 5 and I will pick 2, and this will give me 17. Or I will consider the maximum sum that I can get with the previous 5 guys, which is equal to 15, and I will not pick this coin, but at this time, I will have a sum of 15. Surely 17 is much better. So we go and say that the maximum sum you can have with the coin sequence 5, 1, 2, 10, 6, 2 is equal to 17. Following the constraint, you cannot pick any 2 guys together. Surely when you reach this point, you might be curious about which coins did you collect it. And to get this, what we call this process a backtracking in dynamic programming, you try to trace back to the beginning to find which coins you included. For instance, for this point, so that is 17, right? And you check, is it equal to 15 plus 2 or 15 plus nothing? So that's 15 plus 2. So that means 2 is in the selected coins, okay? So since 2 is in the selected coins, so 6 cannot be, right? So you go to here, okay, so that is 10. Now you are curious if 10 is included in the selected or not. How I can understand it? So that is 15, right? So where did I get this position? Is it equal to 5 plus 10, or is it equal to a direct copy of the previous 7? Surely it is 5 plus 10. Since plus 10, so 10 is included. Since 10 is included, 2 is not included here, right? And you come here. 5, what is this? So that is a direct copy of the previous one. So I should also include this one in my set. So that is 17, and it includes 2, 10, and 5. But observe that to get this result, I needed to trace back to the beginning to detect which coins I'm collecting. Okay, so that's called the backtracking. And here is the short pseudocode of what we have done here. So that is a nice example of a dynamic program. Okay. I would like to have one more example. That's a famous one. I guess many of you might have previously seen this. Okay. So I have some denominations. So these denominations are ordered. So that means D1. So these are integers. Okay, so these integers. such that D1 is less than D2, it's less than D3 up until Dm, and I have this denomination array. And what is my goal is I would like to represent a given number with the minimum denominations. For instance, if n is equal to 6, so let's see how I can write 6. 6 is equal to 1 plus 1 plus 1 plus 1 plus 1. So how many denominations I used? I used 6 of them, right? So what else I can do? I can say that, okay, so that's 3 plus 1 plus 1 plus 1. Now I'm using 4 of them. Or 6 is equal to 4 plus 1 plus 1. So sorry, so this is, so this is 3, okay? And what else I can do? And I can say that 6 is equal to 3 plus 3, so that's equal to 2. And this is the answer I'm seeking for. Good? Okay, so how I can do this? Again, I will be using recursive thinking, okay? So assume you have this optimum number for all the previous guys. You would like to compute Fn. Fn is the number of denominations, number of minimum denominations for Fn, and you don't know this, but you know all the previous one. You know Fn minus 1, you know Fn minus 2. Okay, so you know all the previous ones. Okay. What can happen? So I know my denominations, right? So what I can do is I will go and check what? N minus D1. Okay, so this will give me a position here. So this is N minus, since D1 is the smallest one, so let me try to show it better. Okay, okay. First, I will go to N minus D1, right? And see, I know what Fn minus D1 is, and whatever the number I have at that value, I can just increase this by 1. Why? Because I can just add D1 and get this number. What are the other options? So I can go to N minus D2. I have Fn minus D2. I know the minimum number of denominations to make N minus D2. I can just increase the number of denominations here by 1. Actually, I'm adding D2 to this number, and I'm done, okay? I think you got the idea. Actually, you check all the possible positions prior to Fn, and 1 plus of them will give you the optimum answer. Okay. A good representation is here. So to find the minimum number of denominations for Fn, for n, just go and check all the previous optimum denominations for n minus dj for all possible j values. Okay, surely you should not be falling away from the array. Okay, so again, with this approach, I will need to maintain this array. Okay, so this is my dynamic programming space allocation, dynamic programming array in this case. Okay, let's see, let's run it on an example. We start with f0 is equal to 0. Okay, good. By the way, we are solving the same problem. Okay, so my n is equal to 6, and I have the denominations 1, 3, and 4. Okay, maybe it would be better to write it here. So n is equal to 6, and my denominations are 1, 2, and 4, right? So let me me see. 1, 3, and 4, sorry. So this is 3, 1, 3, and 4. Okay. I start with f0 is equal to 0, and I would like to reach f6. Whenever I reach f6, I'm done. Okay. For 0, it is 0. Now I would like to compute f1. Okay. So 1 minus 1 is equal to 0. I will go to f0 and increment whatever the value I see here by 1. So it is now 1. And that's intuitive, right? So for just value of 1, I have one denomination and I can use it. For 2, since the denominations are 1, 3, and 4, I can go to the previous one, 2 minus 1. Okay, so with the 2 minus 1, I will reach 1, and I can increase this by 1, and that will be equal to 2. Okay, that's intuitive, so that means 1 and 1, so 1 plus 1 is equal to 2. And can I try the other values? No, actually, because I'm at position 2, and if I go back by 3 positions, so this will be out of the array, so that is why I cannot try. But when I reach this position, okay, so 0, 1, 2, they are already filled, and I'm computing f3 now. Okay, so f3, 3 minus 1, yes, I have this, f2, that's equal to 2, okay? And can I make it with 3? Yes, 3 minus 3 is equal to 0, okay? So that's f0, okay? And I have 0 there. So that means 0 plus 1 or 2 plus 1. Surely 0 plus 1 is better. So that is why I have the minimum number of denominations to represent 3 is 1. Actually, it is 3 itself. I think you got the idea. Now we are at position 4. For 4 minus 1 is equal to 3, right? And 4 minus 3 is equal to 1. And 4 minus 4 is equal to 0. I will check this value, and this value. And among these guys, the minimum one is f0 is equal to 0. So I increment it by 1 and get this one. Okay, so you see, we have already checked these values. You keep doing the same for the 5th position. You come to 5. Okay, for 5, I check minus 1, I check minus 3, and I check minus 4. Okay, so I have 1 here, I have 2 here, and I have 1 here. So what would be nice? So ones are the least ones. So that is incrementing either this one or this one will give me 2. Okay. And with the last step, when you go to position 6, 6 minus 1, 6 minus 3, and 6 minus 4. So you have 2 here, you have 1 here, and you have 2 here. Surely 1 plus 1 is equal to 2 will be the minimum amount. So at the end, you conclude that you can represent 6 by using 2 denominations. And what are these denominations? Again, you can just run the backtracking to see first where you came 6 from. And then you keep this tracking until the beginning of the array and get the values. Okay, so let's do it for the first step at least. Okay, so that is 2, right? And that is 2 because I came here from this position, right? From this position. So 3, I came 6 from position 3. So that means denomination 3 is included in the set. Okay, so now you are here. And for that position, where did you came to that position from? So you came it from F0. So that means that is another 3, right? So that is for 6, you need 2 denominations, and it is 3 plus 3. By the way, I should also mention that as you have already observed, while computing F6, I have already computed all the previous results. That means in addition to what F6 is, we have already revealed all the previous ones. So for instance, you can get 4 with 1 coin, 5 with 2 coins, I don't know, 2 with 2 coins, and you can also backtrack these values as well. Okay, so this is the main points that I would like to share with you about the dynamic programming. Surely, in this lecture, we have already observed, studied one-dimensional dynamic programming arrays. With the dynamic programming, it is more common to have two-dimensional matrix solutions. We call them the dynamic programming matrices, and we will see examples of those two-dimensional dynamic programming matrices in our lectures. But for those of you who would like to study in advance, so subset sum or knapsack problems, so these are actually NP-hard problems, and they have a dynamic programming solution. That is another story, interesting. So those are NP-hard problems, and how can I have a polynomial time solution? But we will see this in the upcoming more advanced lectures. Okay, so these are actually called the pseudo-polynomial solutions. And what else? String matching. String matching. So I give you two strings, and I would like you to change string 1 to string 2 with minimum number of added operations. So this is another thing, another dynamic programming exercise that we need to study, and we'll be doing that in the next lectures. Okay. But moral of the story: dynamic programming, it is solving the problem by solving its subproblems that have significant overlaps. Okay. See you in the class, and have a nice weekend.